right, welcome back. So this is the second video on logic. This one will be a bit shorter than the first one, but this one will cover propositional functions and quantifiers. So propositional functions are just sentences that involve a variable, and the value of the variable determines the truth of the sentence. So it turns it into a statement once you specify a particular value of x. So propositional functions themselves are not statements because their truth value is ambiguous. It depends on x. Let me give you an example of this. This first example that we have right here, we have a propositional function p of x, which is the sentence x squared plus 3x plus 2 equals 0. Now that sentence doesn't have any particular truth value. It depends on the value of x that you put in there. So for example, we could look at p of 0. Well, p of 0 is a statement, 0 squared plus 3 times 0 plus 2 equals 0, which of course is equivalent to the statement 2 equals 0, which is false. On the other hand, we could look at p of negative 1, and that's the sentence which reads negative 1 squared plus 3 times negative 1 plus 2 equals 0, which whenever you reduce the left-hand side of that equation, it becomes 0 equals 0, which of course is true. So as you can see, the value of x that you choose determines the truth value, and so the p of x is not always true or always false. It can be both. So that's an example of a propositional function. We want to deal with statements because we want to do things with logic. So propositional functions aren't themselves mathematical statements, but we can turn them into propositional functions using what are called quantifiers. So the job of a quantifier is basically to specify what values of x you're talking about. And we really only have two kinds of quantifiers. The first type is called an existential quantifier. So an existential quantifier is a way of reining in what value of x you're talking, or how many values of x you're talking about. So these are phrases that are equivalent to saying something like there exists. And we have a symbol for that. The symbol for there exists is a backwards e. If I would say backwards e x, p of x, that reads there exists some x such that p of x is true. So if you think about it, that takes the p of x, which is just a propositional function, which could be true or false, and if you say there exists some x such that that p of x is true, that total statement is something that is just true or false, but not both. There either exists such an x or there doesn't exist such an x, okay? So this is really important because, when you think about equations, we often wonder, does there exist a solution to an equation? There are lots of different kinds of existence questions in mathematics. So that's a pretty important quantifier. And the other quantifier that we focus on is called the universal quantifier. So this is when you start asking, is that propositional function p of x always true? Is it universally true? So the universal quantifier is, in English, just the statement of the form for all or for every, something like that. There's different ways to say it. We'll talk about that in a minute. So for all. And symbolically, our symbol for that phrase for all is an upside down A. So whenever you see for every x, p of x, that reads for all x, p of x is true. There are several different ways to say for every or there exists. So focusing here on the existential quantifier, well, you can say there exists, or you could say there are, or you could say for some. You might even say something like at least one value of x satisfies some property. There are lots of ways you could say it, but the meaning of it's clear. It's just saying, this thing that you're talking about, p of x, is true for some value of x. It doesn't specify exactly how many, but at least one. Okay, and we can also word the universal quantifier in a lot of different ways. We can say for each, we can say for every, we can say for all, And sometimes we even say it in sort of a negative form. If you say something is never true, that's a form of for all. So if you say no value of x satisfies blah, 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 then that's sort of a universal quantification in a negative form. Sometimes these things are very clear in the language, and sometimes they're sort of hidden. So we'll have something called hidden quantifiers, where it's just sort of implicit and you're just expected to pick up on, oh yeah, they were talking about a universal quantifier here. One thing that's important when you're doing quantification is knowing that there has to be some universe of values from which x comes. So if x is your variable, I mean, maybe, depending on the situation, you just understand that, well, x has to be a real number here. But if you're taking a different class, like, for example, complex variables, then you would understand that, oh, if the variable x here is going to be a complex number. The universe can change the truth of a quantified statement. A certain statement could be true in one universe of x values, but false in another universe of x values. And like I said, a lot of the times the universe is sort of implicit and just understood from the context, and you don't go around explicitly stating it all the time. To be on the safe side, I like to go ahead and state what the universe is. Let me give you an example of this sort of thing. Consider this quantified statement: for every x, x squared is greater than or equal to 0. If x is understood to be a real number, the statement is true. On the other hand, if x is understood to be a complex number, it is false. So for example, if x is equal to I, the imaginary unit, which you can think of as the square root of -1, then x squared equals -1, which is less than 0. So that shows you that it's not true for every complex number that x squared has to be positive, because I've just given you an example where it's negative. What we can do to specify a universe in our notation is to do something like this. You can say, for every x in the reals, x squared is greater than or equal to 0. Or if you want to do the statement for complex numbers, you could make the statement for every x in the complex numbers. So there's the symbol for the complex numbers. X squared is greater than or equal to 0. And R here is what we'd call the universal set, or sometimes it's called the universe of discourse. And over here, the universal set is being specified to be the complex numbers. So we can specify the universal set just by stipulating what set our x's come in by using the element symbol there and then putting a set that indicates what our universe is. Okay? So that sort of dials in the statement to what universe you want to talk about. So that makes sense, I hope. And as I alluded to a little earlier, we need to be aware that you can have hidden quantifiers. So what are hidden quantifiers? Well, let me give you a couple of examples. Consider this statement: a quadrilateral has 4 sides. Well, it's sort of implicit there that in this statement, it's a general statement being made about all quadrilaterals, right? So there's sort of a hidden or implicit universal quantifier in this statement. I could make it more explicit by rewording the statement some. I could say, well, here's a more explicit version. For all quadrilaterals, you say capital A for a quadrilateral, A has 4 sides. Okay? Notice that the universe is the set of all quadrilaterals here. So if I had a symbol for the set of all quadrilaterals, I could say, like, maybe it'd be something like this. For every A in Q, where Q is the set of all quadrilaterals, A has 4 sides. Something along those lines, maybe you could say. And then also in the next one, the next example here, the statement is if x is greater than 2, then x squared is greater than 4. Now, in this one, it's sort of implicit that this is talking about all values of x that are greater than 2. So there's sort of an implicit or hidden universal quantifier. There's also sort of an implicit universal set, because whenever you say x is greater than 2, that symbol greater than only really makes sense for certain kinds of number sets. The real numbers, I guess it makes sense for integers and natural numbers too, and even rational numbers, but if I sort of chose the biggest set of numbers for which this makes sense, it would be the real numbers. Like the greater than symbol doesn't make any sense for complex numbers. A way I could make this one more explicit is to use the universal quantifier. So I'd say something like for every x in the reals, x greater than 2 implies x squared greater than 4. Alternatively, I could sort of make an observation here. To say x is a real number, I guess I should have been saying x is greater than 2 there. Apologies. If I take those two bits of information right there, really, that's just a long-winded way of saying that the universe, the values of x that are under consideration are all of those real numbers that are greater than 2. So what I could do is I could shorten this up to something like this. For every x in the interval from 2 to infinity, x squared is greater than 4. Notice that it's no longer an if-then statement, but it would be equivalent. But the main point here was that there was a buried for every in this thing that wasn't stated explicitly, but you can kind of just tell that they must be talking about all such x's, right? Okay, the next topic, which is really important for what we're going to be doing the rest of the way out in this class, is how to negate quantified statements. It's really pretty easy. This fact 1.30 tells you that whenever you're negating a quantified statement, all you do is you flip the quantifier and then you negate the propositional function that follows it. So if you're negating a universally quantified statement, as in part 1, you flip the universal quantifier to an existential quantifier, and then you negate the p of x. And similarly, if you're negating the existential quantifier, as in part 2, you flip the existential quantifier to a universal quantifier and negate p of x. So that's all there is to it. Probably the trickier part is just how do you negate the propositional function. To do that, you'll use tautologies that we had back in that big list of tautologies. That there were several of those tautologies that apply to how you negate an and statement, how you negate an or statement, how you negate an implication, and so on. Let's take a look at a few of these. So we're going to use this fact 1.30 to negate this part A here. Okay, so first of all, let's look at this part A. Let's put it into its symbolic form. The symbolic form of that statement is, okay, for some real number x, so I could write that as there exists an x, and I've got a universe here of real numbers, so I can say x is in R. And then there's just the propositional function, x squared plus 3x plus 2 equals 0. Now, I want to negate it. So if I want to negate the existential, it becomes universal. So that'd be for every x in the reals. And then now I need to negate this bit. So I need to negate it. So the negation of equality is not equals. So this will just be x squared plus 3x plus 2 is not equal to 0. And then I can put this back into English if I like. So the English negation would be for all real numbers x, x squared plus 3x plus 2 does not equal 0. One thing I want to point out is the original statement, for some real number x, x squared plus 3x plus 2 equals 0, that is a true statement because, well, consider x equals -1. When x is equal to -1, then it's true that x squared plus 3x plus 2 equals 0. If you negate a true statement, you would expect to find a false statement. In fact, that's what you have here. The negated statement is false. It's not true that for all real numbers x, x squared plus 3x plus 2 equals 0 because, remember the example, x equals -1. So x equals -1 is a counterexample to that statement that for all real numbers x, x squared plus 3x plus 2 is equal to 0. So this makes some sense. Let's just do a bit more complicated of an example, and then I'll give you some problems to try on your own. Okay, so on this one, let's write down the symbolic form. So the original statement is for all real numbers x, there exists an integer n such that n is greater than x. Now notice that there are two variables, x and n, and each of those variables is separately quantified. For x, the quantifier is for all x. And then separately, we have this quantification, there exists, and that applies to the integer n here. And then over here, this part would be your p of x. Well, it's p of x and n, actually. It's a propositional function that depends on two variables. Okay, so the symbolic form here would be something like for all x, and those are real numbers, so in the reals, there exists an integer n, so backwards e, n in the integers, and there's our symbol for the integers, such that n is greater than x. Okay, so now I want to negate this. I'm going to show you that you can do this in sort of a two-step motion. So if I want to negate all of that, then what I'm going to do is, this first step I'm not really going to do anything but use some grouping symbols to make something very explicit. I could think of this way. For every x in the reals, comma, and then I've got this like, there exists an n in the integers such that n is greater than x. And I'm going to think of this bit is like my p of x, okay? And so how do I negate for every x, p of x? Well, I flip the quantifier, so it becomes there exists an x in the reals. And then we have to negate the p of x, so negate there exists an n in the integers such that n is greater than x. Okay, so now I've got a new quantified statement to negate. And this time I've got my quantifier here, there exists an n, and then this would be my p of n. And then how do you negate there exists an n p of n? Well, it becomes a for every n, and then you negate the p of n. So that's going to look like exist an x in the reals just comes along for the ride. Then it becomes for every n in the integers. Now we've got to negate n is greater than x. If you think about it, the opposite that n is greater than x is that n would be less than or equal to x. So this will be n less than or equal to x when you negate n greater than x. And then that's it. So that's the symbolic form of the negation, and then you can put that back into English. So that becomes there exists some real number x. And after there exists, you usually put a such that or with the property that or something along those lines. Such that for all integers n, and then the finale is n is less than or equal to x. What I really want you to notice though is when you go from the very beginning of this problem to the end, what happened? Well, you just negated the two, you flipped the two quantifiers from what they were originally, and then you negated the the propositional function. So that's all there really was to it. All right, so now what I want you to do a little skills check here, and I would like you to take, maybe 10, 15 minutes, however long it takes you to do it, and I want you to do exactly what I did in the last two examples. Just take the sentence that you're given, put it into a symbolic form, negate it using tautologies in fact 1.30, and then put it back into English. So press pause on the video now and work on these, and then when you're done, come back and we'll work through a couple of them together. All right, welcome back. So let's start with part A. I think what I'll do is I'll do part A and part C with you. For part A, let's write the symbolic form out. Well, as I analyze that sentence there, I see there exists, so I'm seeing a backwards E, and I see integer. I don't see a variable. So one thing I might do as I'm writing this up is to introduce a variable, say n, and then stipulate that that n is even and prime. So my symbolic form will be like this. There exists an integer, n, such that, and then I want to say that n is even and it's prime. So n is even, and I'll use the symbol for and, n is prime, like so. And now I'm going to look at the negation. Okay, when I negate existential quantifiers, they become universal. So for every n in integers, and now I need to do negation of n is even and n is prime. Now, I remember De Morgan's law for negating and statements says that that would be the negation of the individual pieces, and becomes or, and then we negate the next piece, n is prime. Okay, and so simplifying that out just a little bit, this becomes for every n in the integers. Well, what's the opposite of n is even? Well, when you're in the land of integers, if you're not even, then you must be odd. So n is odd, or, and when you're talking about integers, if you're not a prime integer, you must be composite. And so putting that into its English form, for all integers n is odd, or n is composite. Should use the symbol there for or. Anyway, as you can see, what happens here is that you apply the 1.3 to flip the quantifier and negate the propositional function. But then in negating the propositional function, you may need to use some tautologies that you learned previously in the big long list of tautologies, specifically the ones that tell you equivalent forms of negating things. So part C, its symbolic form. Okay, let's go to the top here and kind of analyze what we see there a little bit. So first of all, I see a for every right here. I see real numbers that are positive. Then I see there exists, and then I see real number again for a universe. Positive real numbers, actually. Such that then I see another for all. So there's a for every, get real numbers. And then I see the propositional function over here, p of x. And it's a if-then statement. So let's write that down. So it looks like for every, I'm just going to say epsilon greater than 0, and it'll be understood by saying epsilon is greater than 0 that we're talking about real numbers. Then there exists a delta greater than 0, such that for all real numbers, x, so that'd be for every x in the reals, this time it's not specified that x is negative or positive or whatever, just a real number. And then we got this if-then statement, absolute value of x minus 2 being less than delta implies absolute value of f of x minus 6 is less than epsilon. Okay, so now we've got a little room to work here. We want to negate this. So let's think of this as in a series of stages. Well, you may remember we had an example that says, we did an example that had two quantifiers just a little while ago, and I pointed out that the net result when we went from the original to the final form of the negation was that all that happened was that you just flip the quantifiers, and then you negate the propositional function. So the quantifiers here just got flipped from what they were originally, right? And then this thing just got negated. So same idea here. You could break it into a big multi-stage process, but we know that what's going to happen is you just flip all the quantifiers. So it becomes there exists epsilon greater than 0. Now, by the way, before I go any further in this, notice that I didn't mess around with epsilon being greater than 0. All that's the universe, right? Epsilon greater than 0, the universe is like the interval from 0 to infinity on the real number line. You don't somehow negate the universe. The universe stays whatever the universe is, okay? So it's a common mistake that students will do something like, well, there exists epsilon greater than or equal, or rather, there exists an epsilon less than or equal to 0. They'll try to negate the less than or the greater than here. But don't do that. All this whole statement is specifying a universe of real numbers. Okay, so don't negate the universe. You do flip the quantifier though. For every becomes there exists, and then the next exist becomes a for every, so it's for every delta greater than 0. Again, don't change that inequality. That's not part of something that you negate. And then there exists an x in the real numbers. Again, the universe just stays the real numbers. Now we're going to negate this implication. Okay, so now I want to break that down a little further, and I want to just remember that you can negate implication like this. So here at the bottom, I'll remind you, we have a tautology that says that the negation of P implies Q is logically equivalent to, you have the P by itself, and then it becomes an and then not Q. So the negation of P implies Q is the same as P and not Q. And so I'm going to take advantage of that tautology and apply it to this implication right here. So let's do that. So the negation becomes, okay, let me jot down all the quantification part. We're done with the quantification part. We just have to bring it along for the ride at this point. So now we're focused on negating the propositional function. So that becomes, in that tautology that I just wrote down, this is your P, and this is your Q. So it's P and not Q. So it'd be like this. Absolute value of x minus 2 is less than delta, so P left alone. Then it becomes and then not Q, you just have to flip the inequality. So this becomes f of x minus 6 in absolute value is greater than or equal to epsilon. So that's sort of the final form of our symbolic negation. And so let's convert that back into English. There exists epsilon greater than 0 such that, always a such that or with the property that or something like that after the there exists part, such that for all delta greater than 0, there exists some real number x, such that, again, such that follows the existential quantifier, such that absolute x minus 2 is less than delta, and absolute f of x minus 6 is greater than or equal to epsilon. Now you may be thinking that I'm just making up some silly mumbo jumbo here, but this is actually the technical definition of something that you're going to run into when you take analysis class. In fact, exactly what this is, the original statement is what it means to say that the limit as x approaches 2 of some function f of x is equal to 6. So when you take analysis class and you get into the hardcore definition of what limit means, you're going to be working with this definition, just like that. And you sometimes have to work with the negation of that definition if you're doing what we call an indirect proof. Indirect proofs involve negating the original statement. So, yeah, this isn't just some pie in the sky example here. This is something you actually will be working with soon in your mathematical careers. All right. Well, I think that's all I want to talk about with respect to logic, and that will take us up to the next section that I want to talk about, which is mathematical proofs. So we have all the logic that we need now. What's really important in what we've learned so far is basically the sort of thing we did in this very last example. So when you need to prove something, you need to sort of be able to break it down into its logical form so that you really understand what the logic of the expression is. And that can be tricky because there might be hidden quantifiers. The universal set may be implicit and you have to sort of tease that out, what exactly that is. And then you may have to negate some things in order to do the kind of proof that you want to do. So you need to be able to negate the statement, whether it's quantified or unquantified. And so that means that you need to have some familiarity with those tautologies that tell you how to negate things. So, but really, if you've got that down, you're feeling pretty good about this, then you've got everything you need in order to do mathematical proofs. So let me stop there, and in the next video, we'll start our journey on mathematical proofs. And we'll see you then. Bye now.